you very much for this kind introduction. What I'll be talking today about is on vibration problems in lift and escalator systems. And I would like to present some techniques, and this will involve how you analyze and how we mitigate the problems. Okay, the background for this talk is that we have been involved at the University of Northampton in this area for some time now, and we have a specialist group and a laboratory to conduct work in this area. Okay, so here's a brief outline. I'll give some introduction to the problem of dynamics and vibration, and also I will discuss what is causing vibration in lift and escalator systems, about some methods of analysis. I will present some case studies. The case study will be on lifts, and later some issues in escalators, and come up with brief conclusions. Okay, first about standards. In terms of vibration and dynamic analysis, we are talking about the issues of ride quality in lift systems and escalators. There's no actual standard which would tell us what it means there's a good ride quality. However, we have standards which tell us how to measure ride quality. And it is in lifts and in lifts, part 1 and part 2 in escalators. And what is important is that the ride quality issue is linked to vibrations. So first of all, if we have an excessive sound level and vibration, we have a problem with ride quality both in escalators and lifts. How we can define vibration? Okay, vibration is a motion which repeats itself after an interval of time. Typically, it is a simplified definition, but often the complex vibration does not often repeat itself. We have this type of definition in ISO 18738-1. This standard tells us that variation with time of the magnitude of acceleration, when the magnitude is alternately greater and smaller than the average acceleration of the lift, when no lift motion is present, is vibration. ISO 18738-2 gives similar but shorter definition. Okay, so we measure vibration through level of acceleration. However, very often we are concerned also with velocity and with displacement. And we know that the ride quality is affected by jerk. So we have a number of parameters to contribute to how we assess the influence on vibration on ride quality and what we feel in the lift. We measure acceleration in meter per second squared, or milli-Gs, in velocity meter per second, and typically the displacement meters. When we have a vibrating system, and here's a very simple spring and mass arrangement. When we disturb the mass, it will move periodically. And typically, we'll see this kind of motion will repeat itself over time. And this repetition time we call periodic time. The periodic time can be linked to the frequency. And this is where the real issue is the frequency issue. In some ranges of frequencies, we have the issue of ride quality. In another range, we might not feel vibration. However, it still can affect the structural integrity of the system. And we have two frequencies we need to consider in the system, whether it is lift or escalator, in fact, in any mechanical or electromechanical system. Those are the natural frequency and the frequency of the excitation. The natural frequency is when this mass will vibrate freely without any force applied. When you have, however, force, like here, and this force is periodic, we need to know the frequency of this force. The problem is when there's a specific relationship between the excitation frequency and the natural frequency. Okay, so the causes of vibration in lift and escalator systems. I briefly listed here a number of those. We have the inertial load caused by the time profile of the lift movement. When the lift moves from the lower level to higher level to lower level. And this is typically referred to as velocity or acceleration, deceleration profile. We have guiding system in lifts, and those can be regular, and they introduce excitation to the lift car. As we will later show, there are systems which have a number of pulleys, and always there is in traction lift one sheave, and when you have an eccentric or unbalanced defect in the system, they will cause vibration. We can have a systematic resonance in control, electronic system, and we know, for example, that the issue of torque ripple is the issue. We have other faults in the machine, gear systems. In some cases, in older lifts, when we were drum, there was a coiling mechanics which could cause vibration. Now those lifts do not exist, but for the record. And also we have aerodynamic effects. When the lift car moves within the shaft at speed, we have turbulence, and this is causing force, which is acting upon the entire system. And the last, not the least, we have the sway of buildings due to the wind or earthquake. Okay, so first let's address what is happening in the lift. When the lift is moving in the shaft, typically we have this kind of pattern. The vibration is transient. It changes with the lift motion. The reason for this is that a lift system is a non-stationary system. The stiffness and damping in the system is changing. And then when you have a transient frequencies present and we have excitation present, the interaction between the excitation and the natural frequency of the system is causing that vibration happens at a specific time. It could be at the top of the shaft, it could be also at the bottom of the shaft. Okay, so let's talk about the methods of analysis. The methods which I would like to mention here are two types, analytical or computational and experimental. In terms of analytical and computational, we have a modeling and simulation. So typically what we have, if we have a mechanical system and this lift car suspended on ropes, hoist ropes, we can represent this as a model. And the model normally would be consisting of a mass on some spring elements and possibly some damping elements. And this is a simple possible model which you could use. We refer to this as a single degree of freedom model. Namely, you have one mass, and the position of this mass can be defined by one parameter. It is here Q, which could be displacement in meters, for example. So spring mass model can represent a lift car suspended on hoist ropes. Simple representation and very effective when we want to do some calculation or modeling to identify qualitative behavior of the system. Okay, mathematics. This is the equation which describes the system. It is differential equations. In this type of modeling, we refer to as a continuous modeling, and the system changes its behavior. We refer to this behavior as the response, and is governed by this equation. We can solve this equation for the unknown quantity Q, which is the response. If we know this force, and typically if this force is harmonic, it will have two components. This is the frequency omega and the magnitude. We can also calculate the natural frequency. And when the frequency calculated from this equation, from the left-hand side, equals to omega, we have resonance. And I will talk about this phenomenon very briefly a bit later. Okay, now, so we have a model. We can apply the model. We can do some calculations to predict some fundamental behavior of the system. However, we often need to support those calculations by experiments, by tests. And in tests, what we use some techniques to analyze the behavior of the system in time domain and the frequency domain. This is called dynamic signal processing. Dynamic signal analysis tools include one very important technique, which is fast Fourier transform. What it does, it is an algorithm, mathematical algorithm, which allows us to convert time data into the frequency data. And then we have a frequency data, we can create the frequency spectrums plot. And what it is the plot of amplitude of vibration signal or any dynamic signal versus frequency, as opposed to time domain when we plot, for example, acceleration against time. So here's a quick example. How we apply the FFT. There are two plots here. Left-hand side shows a very simple signal. And this could be vibration of this mass on the spring, could be a car. And it moves like this, harmonically. It is sine or cosine. And you can clearly see it repeats itself, this motion, as I shown earlier on. When we do FFT of this signal, we'll see here's the amplitude, frequency, here's the amplitude, time, and from processing this signal, we get a peak, which indicates one frequency value. This is a sign of periodic time corresponding to the frequency of 10 Hertz. And this is a peak 10 Hertz. Easy. So when we see and measure this, no problem. We can identify the frequency, we can identify the magnitude. However, real life is more complicated. When you have signal of this type, well, we see how the amplitude of the vibration, but what is the frequency? From which we could calculate, when we take these 2 points, we can calculate or measure time inverted, get the frequency. Here, we need to do FFT, and FFT tells us what is the main component. And again, in this example, I took this wave sign and including some noise, and from this noise, which is here background, is still present 10 Hertz. And very often you would see this type of signal when you put your PMT or an accelerometer in the lift car. And you have to do FFT, which most of us know. Okay, now is a case study. Okay, this case study I chose because it comes from latest test which we did on a lift car in the lift system which has been wrote 4-2-1. And this is to demonstrate what kind of problem you will have here and how can you detect the problem. How we analyze and later diagnose and fix it. And the fix in this case will be quite simple. Okay, what we have a heavy car, and this is suspended on a suspension rope which goes through a number of pulleys, 4-2-1. 4-2-1 is prone to have a lot of pulleys, and when they have a problem with the pulleys, they cause vibration. Okay, so what we do first, we need to identify some key parameters of such a lift system. And this will be typically velocity of the car and diameters of the pulleys. And when we have this, we can calculate the frequencies which correspond to rotation of the pulleys. 1, 2, 3, 4, 5. Here's a set of 2, set of 2, set of 2. Calculation is very simple. We do kinematic analysis. So essentially the frequency omega is equal velocity divided by radius. And you have, in this case, the pulleys rotate with 1, 2, 3, 4 frequencies. 5, this is about, values range from quite low, when we have the first pulley is about 0.8 Hertz. The next will be multiply this by 2, 1.6, multiply this by 3, 2.4, times 4, 3.2, and 3.2. Okay, so we've got the frequency in the system. And now we do a bit of modeling. Okay, we take the car, we suspend it on the spring, so we have a mass spring system. We can calculate the natural frequency of this system from a simple equation, which is square root stiffness divided by mass. Okay, the trick is that we need to take effective stiffness of the entire roping and also effective mass, which is involved in vibration. If we are talking about the effective stiffness, will be, okay, number of branches of rope. Effective mass, we need to take into account, for example, masses of ropes. And there's a formula for that. And we calculate. And then we need to calculate this over the range of travel height. So the length of the ropes change, and here I have two curves calculated from this equation. The first curve is empty car, dashed, solid is with rated load. And the calculations come from this equation, where obviously we change, okay, when the length of the ropes change, the frequency changes because it affects the stiffness. So, for example, when the car is at the top level, high frequency, on the lower level, lower frequency. And here's the frequency which we, at some stage, calculated as a 3.2 hertz. And then you go back to my previous slide. Here's 3.2 hertz. So we are on the track. Okay, now, calculation. Now we need to do some measurements. Ideally, you need to do a test to identify whether the calculated value of 3.2 hertz is true value. The test could be very simple. You take a car, you can jump inside and stick accelerometer to the floor, measure the time domain response. It is now acceleration here. And we see the cars are starting to jump and settles down. Take FFT, and we've got a peak 3.1 to 5. Close. We calculate 3.2, here's 3.1 to 5. We are on track. Okay, so what do we next? We look again at the bigger picture. We look at how this system is, in terms of frequency, behaves. We run the car, we take the measurement during the car, let's say, vibrating at a specific level. In this case, it was the bottom level loaded. This is the signal which I showed you earlier on, quite polluted. You cannot see frequency. You do have FT here on this signal, and you have peaks, frequency peaks. So this is the frequency about, we look at this point, this frequency, 3.2, and this is 6 times of F2, frequency of these pulleys. And that's what's shown on the spectrum. Now what do we do next? Okay, when you have those, we confirm through calculations and experimental tests, we are able to pinpoint the problem. Okay, there are a number of pulleys. We know that the pulleys which have the frequency F1, F2 might be the reason. Those were pulleys who are made of polymeric material. And what is more, they had reinforcements. Here's the pulley. It has got reinforcements here. 6. Okay, we go back here. 6 times F2. So that means that we have to pinpoint one set of pulleys which has got frequency F2 and 6 reinforcement. And this was this set of pulleys here. This frequency here is responsible for another problem. And what eventually was found, that the pulleys were deformed. They were deformed between reinforcement. And the deformment, out of roundness error was quite substantial, from 0.211 millimeters to about 0.3 millimeters. What it caused? It caused out of balance excitation and was periodic. And there are some additional acceleration forces involved. And this caused excitation and resonance. Mitigation, replace the pulley. So there is an example when you have a very simple mitigation strategy. You do analysis, you find the reason, and you fix it. For example, replace the pulley. Sometimes it might be simpler. In simple case, you can balance the pulley. Okay. Now, the second case study is when we have a bit more involved system. And the mitigation strategy could be more difficult. And this is dynamics of car suspension and compensating ropes. Typically, we have three types of vibration in ropes, in cables, in lift systems, in the vertical direction, lateral in plane, so that means this plane, and lateral out of plane. Those three types can interact with each other. Okay, now in this case study, I will take one type of behavior of the building and lift systems in terms of their dynamics. Tall buildings sway at low frequencies. When they sway, they transfer motion to the lift system. Typically would be a car or counterweight, and the system is being excited, starts to vibrate, and what you will see what vibrates, typically compensating ropes, which, as you know, in tall buildings, they have to be to balance masses of hoist ropes. And the compensating rope, here's a counterweight, here's a car, set of ropes, and tensioned by the weight, compensating pulley assembly. Okay, now, so what do we do? We do modeling, okay? Again, we do the same approach, modeling. However, modeling in this case is more complicated. The behavior of the system is not governed by one differential equation, but is governed by a set. Those equations are, we refer to them as the partial differential equations. They are nonlinear, and nonlinear means that the behavior of the system is more complex. Okay, here's a typical arrangement: car, counterweight, cable going or rope going from the car side down to the compensating sheaf and to the counterweight. The length of these cables change. Do the calculations, and here's a brief demonstration of what happens. This is a motion of the compensating rope at mid-span, which behaves initially, well, in this case we have displacements in two directions. In out of plane, that means this direction, and in plane. And what happens is this kind of behavior. The rope starts circular motion. So this is a building with the height of measured from here to the top, and sways, and the rope moves. Okay, and then there's a problem. We have not solved fully this problem. It is current PhD project. Okay, so now mitigating strategy, what will it be? Okay, replace the ropes? No, it will not work. No, we have to apply something different. So what we need to do is to find how to damp vibrations using either passive or active methods. Okay, passive methods means that you include a damping element into the system. However, ropes move, hardly you can attach to them anything. We need to apply active damping or active vibration control strategy. And in case of the compensating rope system, what could be done is to apply the concept of active stiffness. What it means is that in this system here we have compensating sheaf here, rope vibrating, let's say at one side, car, counterweight, and we pull this mass at the bottom with, for example, twice the frequency of vibration of this rope, 90 degrees out of phase. And this sort of a pulling motion can damp vibration of the ropes. Here's mathematics of it. What is in this equation is the implementation of a feedback control. When we have motion here, it is informed by some input from the measurement of the response. We measure the response, we feed the measurement to a control algorithm. The control algorithm applies this motion. We don't damp vibrations. Okay, here's an example. In this case study, it comes from numerical simulation. Height of the building, frequency. This is 0.1 hertz. Here's the frequency of the fundamental of frequency of the cable. Here's the second frequency of the cable, because in the cable we have actually plenty of frequencies. What we do concentrate are on the lowest level. At this point, these lines intersect, we have resonance. And the issue is that at resonance, you see this motion, circular motion. Okay, what happens? The black curves is when we see the rope again. This is height of the shaft. Here is amplitude. The rope can vibrate without damping quite a lot. Now we apply active damping, we dump the system. Okay, mitigation strategy, but a complex. I move on into escalator system. Escalator or moving walks are different machines than lifts. However, there are some common features. And I will concentrate on some common features here, and we demonstrate that some vibration phenomena in escalators are actually quite related to what we have in elevator systems. I still have some time probably. What is escalator or moving walk? It is a machine which is typically chain driven, and there is an interaction between the chain and sprocket, which is often the main source of vibration, not the only one. However, in addition, we have other causes. Okay, moving steps, rotating unbalance, so we have pulleys which can be misaligned. We have some torsional loading due to motor drive, and typically any other cause which you could see in any other machine. An escalator is a multi-dynamic system typically consisting of hundreds of elements. So everything moves. So let's have a look now at one little part of this is a chain. So typically when we take two sprockets and one is driving sprocket, the other one is tensioning sprocket, we have a chain going over. In fact, we have a quite similar system what we saw about rope and elevator in compensating ropes and suspension ropes in elevators. Okay, this has, however, is slightly differently configured. The chain is moving in a path which is not straight line, and the chain has got discrete components. In fact, it is becoming quite complex system. What happens here is that in terms of chain dynamics, we have discrete nature of links. In the cable rope, the rope is a continuous member. Here we have discrete parts. And what it does to the system is that when we have impacts and any other phenomena between the roller and tooth, this is being caused, it results in vibration and excessive noise. Okay, we'll be talking here about transverse vibration of the chain, which can be caused by any internal or external features. What is external would be, again, something which is unbalanced, and we have a periodic torsional loading into the system. Okay, so let's have a closer look at the chain dynamics. We do again some analysis. So we do some calculations. And the first calculation is very simple. When we have a chain moving, we have the speed of the wheels or sprockets. We take the speed, divide by 60, and we multiply by the number of teeth. We get the frequencies which are present in the system. And depending on the number of sprockets, we have a different frequencies. Then what we do next, we calculate the natural frequencies of the chain. And this is coming from a very simple formula. N pi over L square root tension divided by mass per unit length of the chain. And when those two frequencies coincide, we have resonance. Okay, similar what we had in a lift system. Here's another model which we could apply now to analyze the chain dynamics in more detail. So we have a chain. it moves over the sprockets, and we have vertical vibration. This vibration can be described by mathematics. And what is important here, that in this equation, which is now quite complex equation, similar to what we had for a cable or rope, has got fluctuating tension force. And one reason that this component is there is so-called polygonal action of the chain. Okay, why polygonal action? When you look at this shape here, it is a polygon. And this action is due to the fact that the chain on this sprocket forms a polygon rather than a circle. And this leads to fluctuation of tension forces and velocities. What we have on top of that, we've had impacts between the teeth and the chain elements. And this term is being generated. Okay, how we deal with this? Here's a very simple calculation which can be done. When we have a polygon, and we can draw this polygon, in this case is in the case when we have 6 teeth on the sprocket. We can calculate the maximum value of the chain, which moves in this or the other direction, by knowing the rotational speed of the pulley. When you multiply this by this larger radius, we get the maximum value of velocity. On the other hand, when the chain moves a bit further, the velocity is expressed through the same frequency, but the smaller radius. And what we have different velocities which fluctuates. And the ratio between the speed of change can be calculated as a difference between those two velocities and rated dividing by the maximum velocity. And what we get from this simple formula. And when we plot this curve, we have the number of teeth and the speed of variation. So this parameter, number of teeth, we see that when we increase the number of teeth, we have less fluctuation. What it means is that when the chain is vibrating according to the fluctuation of the speed, the vibration can be reduced if the number of teeth is increased. So this is the simplest mitigating strategy. On the other hand, it doesn't always work. We need to apply a number of additional measures. And typically what can be done, we apply some guiding features into the system. Our current work is modeling and simulation, and as well as experimental test on elevator chains. And this is to accommodate the problem of fluctuation of speed due to polygonal action, as well as impact of teeth between the sprockets. This work is supported by MSC company, which is a developer of Adam's suite of analysis and modeling software. Okay, so now as brief conclusion, I have a couple of points to make. The challenge for engineering practitioners and researchers who work in the area of modern vertical transportation is to design a system which provides efficient and safe service. We know that both elevators and escalators suffer from vibrations, and the difficult part is that we have a complexity in the system. That means the tensions change, the masses change, the length of elements change, and this renders the system with time variant parameters. We call them non-stationary. When we apply modeling and analytical methods, and later employ computers, and we combine them with experiments and dynamic signal processing, we can develop mitigating strategies. Sometimes they are simple, but more often not. So we can apply passive or active vibration suppression methods. In terms of an elevator and escalator system, typically passive systems do not cover all frequencies. Therefore, we need to apply systems which are referred to as active vibration control. I would like to acknowledge support from ThyssenKrupp and to allow me to present some examples of the problems which I analyzed. And I would like to thank you for your attention.